Alright, hello and welcome to another episode of How to Understand X. Today we're going to talk about set theory. Disclaimer, I am not good at set theory. I took a summer class and on my first test I did not do so hot. But I find set theory super fascinating and I will link to, better sources and, more probably accurate videos, but I do want to talk about set theory because I genuinely really like it, and it does have quite a bit of applications in the rest of mathematics as a whole. Um, without being too melodramatic, I would say that set theory is math, the mathematical study of math. You know, you can use set theory in almost every other field of study in mathematics, and you need set theory for every other field of mathematics. That's calculus, that's like geometry, that's algebra. Set theory is what gives math the bounds that it needs to, make any sense at all. So yeah, let's split set theory into two words, and then we'll talk about each of them. Set and theory. Now, a set is pretty much anything. In terms of math, it's going to be an organization of numbers, but a set can also be letters. It can be words. It can be almost anything. It's just an organization, or perhaps even a collection, of things called elements that have something in common. Each set is considered well determined when each of these elements have something in common. For example, the set 1, 9, and 10,000, let's even make it 10 million, is a well-determined set if this is a set of three numbers. That is the that's the thing that they have in common. They are all positive, whole, natural numbers. That would be a subset of n. And that word, subset, that was a very awful n. It's supposed to be n and then like a fancy thing, and that is called the set of natural numbers, or essentially every positive whole number, and 1, 9, 10 million, was that the set? I forget. But yeah, that is going to be a subset of n. But I'm getting a little bit ahead of myself. Essentially, a set is just a collection of elements that have something in common. And then theory is a little bit more tangible. A theory, well, not a theory, but theory in this meaning means it's just the properties of sets and how you can define these properties and manipulate them. So yeah, set theory. I mean, it sounds fancy, but I promise it's not super difficult. And we're going to talk about some vocabulary first. I mentioned beforehand, just so that we can, jump straight into actual set theory. A set is a well determined, that means they have something in common that is explicitly defined, a well determined collection of things called elements. And elements are just going to be the members of a set. I know that seems kind of like a circular reasoning, but I feel like this is relatively self explanatory. Members of a set. And then, yeah, there's also a term cardinality. Informally, we're going to refer to cardinality as the number of elements in a set, and that is denoted by lines. For example, if I wanted to say the cardinality of A, I would just put two lines around A. if A is a set. So yeah, you can write that down if you want, or just, keep it in your head. And a subset is a term for a set that, let's say, houses all of its elements. Houses is actually not a great word. How would I define subset? I could just say that a subset is a set that also exists within another set. Even though that's an inaccurate definition, I think it'll make sense in just a second. So a subset is when we're going to use two sets, A and B. These are, again, going to be well-determined collections of elements. So A and B are two sets. A is considered a subset of B. This is going to be the denotation. It looks kind of like a C. Well, I mean, I wrote it incorrectly, but it's like a flat C, like that. Like a sideways uppercase U. That's the best way to put it. So, yes, A is considered a subset of B when every element of A is in B. For example, if A is equal to the set 1, 2, 3, 4, and this is going to be determined as a set of 4 elements in the set of natural numbers, then A is going to be a subset of the set of natural numbers because each of these exist in, 1, 2, 3, 4, 5, dot, 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 and then, on and on, 6, 7, dot, dot, dot. And that's going to be the set of natural numbers. Since every element of A, there's only 4 of them, is in the infinite set of natural numbers, because you can just keep on going, A is considered a subset of N. But, subsets can be of finite sets. So B could be like 1, 2, 3, 4, 5. And every element of A, 1, 2, 3, 4, is in B. And while 1, 2, 3, 4 is in 1, 2, 3, 4, 5, 1, 2, 3, 4, 5 is not in 1, 2, 3, 4. Subsets have to be either smaller in cardinality or equal in cardinality. So, for example, if B was also 1, 2, 3, 4, every element of A, again, 1, 2, 3, 4, is in B, 1, 2, 3, 4. But every element of B, 1, 2, 3, 4, is in every element of A, 1, 2, 3, 4. So every set is a subset of itself. So again, a subset is just a set that has a certain number of elements that exists within another set that is well defined. And on that note of every set is a subset of itself, the empty set, or this, you might have seen it before, empty set, it's just, 2 brackets. There's nothing in. 0 is a set, but it is not equal to the empty set. 0 is an element. It's not a natural number, but it is an integer. So 0 would be a member of a subset of Z, which is integers. So, yeah, while 0 isn't a natural number, it is an element. So this set has, let's even define this as A. The cardinality of A is going to be 1. There is one element. But the cardinality of the empty set is nothing. There is no elements in the empty set. So every set has the empty set as a subset. So 1, 2, 3, 4. The empty set is a subset of 1, 2, 3, 4. Even though, nothing is not explicitly defined in that 1, 2, 3, 4 nothing, it's just implied that the empty set is a subset of every set. And this is more, just, you won't need to know this too much. I don't think you will, but the power set is the set of all subsets of some set. So that sounds complicated, but I promise you it's probably not going to have too much application. We're going to say that the set 1, 2, 3 is A. The power set of A is going to be the set 1, then the set 2, then the set 3, then the set 1, 2, then the set 2, 3, then the set 1, 2, 3, then the empty set. So those are all the possible subsets. It is every element individually. It is every assembly of the every other element, and it is the set itself and the empty set. That is the power set of any given set. And yeah, I think that's relatively self-explanatory. Once you get to, larger sets than maybe 1, 2, 3, you're going to see extremely large power sets. But yeah, and I think that's essentially it. We will also need to do some like writing things. So this symbol, this symbol right there, kind of like a E, is implies membership. So if X is an element in X, let's not even use X. I feel like that would be a touch confusing. Let's say A is going to be our set, and then X is a member of A if A includes X in its set. So if it was 1, 2, 3, X, X is going to be in A, and then such that just is used as a transition abbreviation, like it qualifies the A or even defines A as a specific set or defines X as a specific element. It just, it's kind of used as a transition. And then there's also for all. This is an upside down A. So for all is very useful in defining a set. So for all elements, or let's say X, in some set X, there is some property, maybe that X is greater than 1. This is just saying that if X is a set 2, 3, and then 4, for all X, or for every element in big X, X is going to be less than 1. So every element in big X is, not less than, greater than 1. So 2, 3, 4. That would be an accurate statement. So yeah, that's just some, I was about to say vernacular. I'm losing it. I don't know what you'd call that. Symbols, shorthand probably. But yeah. And one last word. We're gonna have axiom. This is something that's assumed to be true. Not because it's obvious or anything, but because it's not possible for us to prove formally. It's just an idea that we hold about all sets in general. So I'm going to start with elementary set theory, but I also want to get into number set theory because that's what I am more, accustomed to. I'm using some sources for this, but I don't know too much actual set theory. I just know number set theory and elementary set theory a lot more. So we're going to go into that a little bit further. But we are going to define ZFC. So ZFC is it's Zermelo-Fraenkel. I think it's just Fraenkel, but Zermelo-Fraenkel set theory. This was one of the first attempts to really codify set theory because before ZFC, which is what this is going to be called, well, ZFC is Zermelo-Fraenkel theory plus the axiom of choice, so C, which we will talk about in a little bit. But ZFC is one of the most influential attempts to codify set theory because, again, sets are very broad things. You can kind of just define a set as any assembly of anything ever. So Zermelo-Fraenkel set theory, specifically for mathematics and like we'll talk about what elements ZFC talks about, but ZFC was one of the first attempts to really come up with some standardized form of set theory. And you know me, I like to use proofs. I like to describe what's happening as best I can. But again, these are axioms. These are things that are assumed to be true because we can't, at least currently, we can't prove these. These are just these are the 10 commandments. Well, there aren't 10, but these are like the commandments of set theory. You can't really contest them because they seem somewhat obvious. So let's get into it. We have extensionality. I'm gonna just list them and define them at the same time. I don't want to list them all and then define them all because I don't want it to be too confusing, but we say that if two sets, A and B, are equal if every element in A is the same as every element in B. I know same is kind of a vague word, but I think it's relatively self-explanatory. One second. Every element in B. So yeah, 1, 2, 3, 4. If that's gonna be A, and B is also the set 1, 2, 3, 4. Every element in A is the same as every element in B. So A equals B. That's called the axiom of extensionality. I know, very fancy word for something self-evident, but yep, that's the axiom of extensionality. And then we also have the null set or the empty set. I like to call it the empty set. We did talk about it. It's going to just be, well, oh, I forgot one last little shorthand. This is going to be there exists. uh, like, I mean, you know, the way we speak, we should just say, like, uh, something exists, and exist is like what the thing is doing, but there exists can be used at the beginning of these kinds of sentences. So, there exists a set that is written like that, that has no elements. That is the axiom of the empty or null set. I'll be referring it to as the empty set. And then we did talk about the power set. I mean, well, almost forgot. We have the pair. Given sets A and B, there exists a set A, B that has the sets A and B as its two elements, and that's it. Like, if you have two sets, you can create a set where those two sets are the members of that set. So, if A is equal to 1, and B is equal to 2, there must exist a set C that has A and B as its elements. So that's going to be the set 1 and then the set 2. So yeah, I mean, again, these are mostly self-evident, so attempting to write some type of formalized proof about it would not give you anything. But pairs can also be helpful in writing proofs, because you can say that for the set A, if, A is equal to some set of something, there is a set A that has every element in A as a set as its element. So, yeah, every set is determined by some type of, like, some type of characteristic. So, if A is going to be the set 1, then there is a set of A that is the set of the element 1. So yeah, I mean, relatively self explanatory. Then we did talk about the power set. Power set is just going to be the set of all subsets of a set. And the way to write the power set is a fancy looking P, goes like that. Okay, that wasn't too bad. The set of, say, A. That's going to be the power set of A. And again, if A is equal to 1, 2, 3, that would be the set 1, the set 2, the set 3, the set 1, 2, the set 2, 3, the set 1, 2, 3, and then the empty set. Okay, so, yep, power set, we did talk about that. And then we get into union. The axiom of union says that for all sets A, there exists a set denoted by union A, whose elements are all the elements of the elements of A. Of A. So that's just saying that, for every set that exists, you can have a set or a union of that set, and the elements of that union is just going to be all the elements of A. So, yeah, like if A is a set of sets, then U is going to be a set of every element in those sets. And, it's relatively self evident. It's pretty similar to the thing that we were talking about with the axiom of the pair. Um, you know, that if you have a set A, then there exists a set of a set A. So, yeah, you know, I know that sounds confusing, but we will do some type of similar example, and I think it'll be relatively, normal. And then we have the axiom of infinity. This one is nice and simple. It just says there exists a set with infinite elements, or even simpler, there is an infinite set. Again, this is an axiom because how can you prove it? Are you going to spend every single waking minute of your life and the lives of every single human in the history of humanity and just keep on doing that until the end of time to prove that infinity exists? Not exactly. So we will set and we will say that the axiom of infinity just allows for an infinite set to exist. And one important idea is that there exists a set, let's say X, where the empty set is element in X. So let me use our right there. So we have where the empty set is a unit of X, and this allows for the idea that A is, if there is a set A, such that a set A that is in X is the union of A and A that's in X. So essentially, if X is infinite, then X will obviously contain the empty set. Well, not obviously, but we have to guess that since the empty set is a subset of every set, then even if there was an infinite set, then X would be, then the empty set would be an element of that set. And then if set A is a finite set, then if you union A with every element in A, then that would still just be a member of X. So if X is infinite, then it'll be the set of all finite sets that are unioned. So yeah, I hope that made sense. I mean, I might be complicating a bit further, but that's just the formal definition of infinity. It's just saying there is an infinite set. Then we have the axiom of separation, and that's for every set. Ooh, funky looking E. For every set A and every characteristic of A, there exists a set containing just every element in A, or exactly the elements of A that have that property. So, I guess informally, so just informally, that's gonna be like, I don't know. It's just saying that like, if you have a set, let's say let me erase that. You can write that down if you'd like. But if you have a set A and you have a set B, where B is a subset of A and X is a member of B, we're going to say that X is also a set. If X is a member of B, then X is going to be a member of A. And this is gonna be, this is called an axiom schema because this is just a collection of an infinite number of axioms. Like, let's say, I'm actually going to use the correct term, that's property. A property is given by a formula it's the letter phi. I'm not super great at writing it, but there we go. Phi of the language of set theory, or the first order language of set theory, and that's the correct term for it, first order language of set theory, and that's what we're speaking right now. And since phi is a formula that is written for every single set that can be conceived, the axiom of separation is in fact an axiom schema, or an infinite list of axioms. So, yeah, I mean that A, B, and X example is probably the extent that you are going to need separation to understand what's happening in it, but, there will be some more in-depth examples of separation, because the axiom schema of separation is important. I mean, all of these are obviously very important, but separation can be a little bit tricky. And replacement. For every defined function, or for every definable function, with a domain of the set A, there is a set whose elements are all the values of that function. And this one's also very important for proofs, even though you don't have to, evoke the axiom of replacement too often, I don't think. For most proofs, I don't think that you need to continually, evoke the axioms over and over again, because, once you get to number set theory, the set of natural numbers specifically, and you look at those axioms, I don't believe that you need to continually re-evoke these axioms, but of all of that function. So this one's essentially saying that if we can even think of it in the xy plane, if y is a function of x, then for every function y that can be defined as a function of x, there exists a set of every y value of that function. So, yeah, for every function that takes a certain input, there is a set that has the output of that function. And replacement is also going to be an axiom schema because every function is different, and there's an infinite number of functions out there for you to create or to see. So, yep, that's the axiom of replacement. And then we have two more. Oh, we have one axiom that is specifically Zermelo-Fraenkel set theory, and that is the axiom of foundation. And that's every non-empty set A contains an element or an membership minimal element where so this membership minimal element, that's just an element where no element of A is in that element. So example, we have A is the set of the set 1 and the set 2. A is non-empty, there are 2 elements in it, and the set of 1 does not have any other element of A in it. So this is a membership minimal element. I'm not sure if it's called a membership minimal element, but that's just how you write it, and that's how I would say it out loud. But yeah, A is, well, not A, but every non-empty A has an element that has no other elements of A in it. That's the axiom of foundation, and that is the end of Zermelo-Fraenkel set theory, or ZF. But I did mention there was a C, and that C is the axiom of choice. So the reason it's not part of ZF is because the axiom of choice was originally somewhat controversial. I mean, it's not controversial now, but I'll get to why it's controversial in just a second. We have the axiom of choice, and that states that for every set A of pairwise disjoint non-empty sets, and disjoint means that the elements are different. Non-empty set, there exists a set that contains exactly one element from each set in A. So that's kind of out there, but like we're gonna use bins and balls because that's I know that sounds ridiculous, but that's kind of how we informally define certain functions. We just like use you know, nonsensical examples. So if you had a selection of one ball, let's say that you have an infinite number of, well, it doesn't even have to be infinite. We just say that we have like 3 boxes, right? I'm going to use boxes instead of bins. So we have 3 boxes, and there is a certain number of balls in each box. Then you can pick one ball from each box, regardless of the number of boxes there are. There is, you know, there could be an infinite number of boxes that you can choose from, but like you will be able to choose one box, and there is going to be a set for like you can put all those balls that you chose from one box into another box. So like say you had, let's say we had infinite boxes, right? And each of these infinite boxes they could either have the same amount of balls or, well, actually, not exactly the same amount of balls. These are pairwise disjoint boxes, so they have different numbers of balls. but they have they have some number of balls. You can take one ball from each box, and at the very end, once you've taken, I mean, this you can't have an end because this is an infinite number of boxes, but theoretically, if you were to take the ball that you took from each box at the very end, you can put that into a box, and that's essentially it. You can do that. That's what the axiom of choice is saying, and it's kind of weird why this is considered controversial. Uh, this was part of like why the wait. Let me think. What's that paradox called? Yeah, it's called the Banach-Tarski. Is it Banach-Tarski? I don't know, but it's the Banach-Tarski paradox, or it might be Banach-Tarski paradox. It just says that if you had a 3D solid, some sphere, you can break that sphere into finitely many very tiny pieces. Um, so it's finite because you have a physical 3D ball, but you can break it into imperceptibly small pieces, and using just rotations, translations. There was a very well done Vsauce video on this, so I'll link that down below. But the Banach-Tarski paradox, let me write that down, is one of the refutations to this axiom, even though, it's the reason why it's not considered like a refutation to the axiom of choice is because even though you could break this 3D spherical object into finitely many very small objects, even if you use a bunch of rotations and translations and make that single ball into two solid balls with the same volume as the original, then there is an illustration of how this works and why this works, but the reason this is not considered a refutation of the axiom of choice is because these are non-measurable sets. This idea that you can break this finite object into finitely many subsets, and then make a completely new set from those original sets, those are non-measurable sets. So you cannot measure how minuscule those shards are going to be. So that's why it's considered a non-measurable set, and it won't be, a refutation of the axiom of choice. But this axiom specifically is just used to establish an object that you can't define. Like we, I mean, you could probably tell by now. Set theory is very broad. It is just the mathematical study of math, right? And of our observable universe. So trying to define things with such a broad framework is pretty difficult. So we can use the axiom of choice to just kind of say that there is a well-ordered set of numbers or objects or anything, and you can use that assumption that there is a set of numbers to, find the properties of those numbers. So yeah, it was originally controversial because they were like, how can you just say that something exists without doing anything for it? The axiom of choice is now used like with abandon. It's very difficult to, just say that something exists without using the axiom of choice because it just essentially says that if there is a set of some elements that have something in common, you can take elements from each of those sets and then make another set out of it. So you can just create an object from another set which may or may not actually exist. So, I mean, it will exist, but you just can't explicitly prove that it exists. So yeah, that's the axiom of choice. And now it is part of ZFC, or the Zermelo-Fraenkel set theory. And yeah, that's pretty much all of the things that we are going to need to know. And we can also talk about union and intersection. This is not the axiom of union, by the way. This is just something that we're going to do. So A union B is when you combine the elements of A with the elements of B. So the set of A union the set of B is just going to be the combination of every element in A with every element in B. And then A intersection B. I probably shouldn't use like the brackets for this, but A intersection B is gonna just be like the set of the elements that are common between A and B. And people tend to remember N and because, A intersection B is just every element that both A and B have in common. And then there is also going to be an ordered pair. So the ordered pair of two sets A and B is going to be the set of A as a set, and then comma A and B. So the ordered pair of A, B is going to be the set of A and the set of A and B. And A, B is equal to CD if A equals C and B equals D. And yeah, that's essentially it for our elementary set theory. I know I didn't like do anything super interesting. I just kind of talked at you for a little bit about what's happening in Zermelo-Fraenkel set theory, but I think it does have some merit to at least look at these proofs, or not these proofs, these axioms, and to just kind of see where the origins of set theory is and see how broad the field is, and where you might even want to, do something of your own and figure out how to define something that people haven't done before. Because, again, set theory is incredibly broad. The axiom of choice, something that is almost absolutely necessary for all math, was considered controversial because it made it too specific. It allowed you to create two things that didn't exist beforehand. And that was considered controversial because the rest of Zermelo-Fraenkel set theory is just letting you do whatever you want. So there is lots of things that are out there to be proved, and I feel like that might not have been the best introduction to set theory. I will put some more sources and ideas, but yeah, that's pretty much it. Oh, I forgot the Cartesian product. That's an A. I don't know why I didn't write it like that. Cartesian. And I don't know why I put an A instead of an O. The Cartesian product of A times B is just going to be the set of all elements, or set of all ordered pairs, excuse me, C, D, where C is an element of A and D is an element of B. So yeah, the Cartesian product is just going to be, like when you do something, if A times B is a explicitly defined function, then you are going to do that function for every possible input of A, that is, well, not every possible input of A, but every input of A that is in A. So, yeah, that's essentially it. Now we can get into some of the crazier stuff. I mean, Cartesian product, it's just, we will talk about it more, but essentially, if you have a function that you have defined, then you will be able to do that function for two sets. If you have a function that has a certain set of inputs and a certain set of outputs, and the Cartesian product will just be the function that is happening, and just the ordered pair of the input and outputs for every possible input. So yeah, and then, oh, I might also need to talk about bijections, injections, and surjections. Yeah. Okay. Looking at my notes for just a second. I did not write a script, but let's talk about bijections actually. So, bijections, injections, and surjections. Um, all right. So, okay. So, in trying to like split these three different things into, terms that we can understand, I first must say that a bijection is both an injection and a surjection. But all three of these are functions. Functions. So they have some input that through some process becomes output. And now let's start with an injective function or an injection. This is a one-to-one function. That's what it's usually called. And it essentially maps distinct elements from your input to your output. So every element of the input function has an output. That doesn't mean that every output has an input, but every input does have an output, so it will be an injection. For example, we can draw a nice little bubble map, I think is what it's called. So let's say that x is going to be our input and y, x is a set of 1, 2, 3 elements, and y is an output of a, b, c, d. If we say that 1 maps to a, 2 maps to b, and 3 maps to c and to d, this is considered an injection. Every input has an output. Oh, sorry. That's not correct. This would be an injection. Every input does have an output, but not every output has an input. That's what a surjection is. So, an injection, there is an input for every output, and a surjection, let me actually write this down. So, injection, input for every output, and surjection is output for every input. So 1 maps to A, 2 maps to B, 3 maps to C. This is an injection. And then if we had an output for every input, then this, if 3 maps to C and to D, then well, actually, we'll talk about that in just a second. We will change our outputs and our inputs and say that x can be, say, 1, 2, 3, 4. And then y can be a, b, c. If 1 maps to a, 2 maps to b, and 3 maps to b, and 4 maps to c as well, then there is not one input for one output. There is 2 inputs for one output, so that would be a surjection but not an injection. And a bijection is both a surjection and an injection. So that means that it is a function with elements between two sets. Function with elements from two sets where where each in the input set, or the set of inputs, corresponds, and you might actually see this called a one-to-one correspondence, where each element in the set of inputs corresponds to an element in the set of outputs. So yeah, it would look something like, let's go back to 1, 2, 3, 4 and A, B, C, D. We have x, y, 1, 2, 3, 4, and then A, B, C, D. If 1 maps to A, 2 maps to B, 3 maps to C, and 4 maps to D, then we have one element for each, one input for each output, and one output for each input. So it is both an injection and a surjection. And lastly, a function that has 2 inputs for one output. Let's see what that would look like. But not every output has an input. Like say we go back to 1, 2, 3, 4, and then A, B, C, D. If we have 1 maps to A, 2 maps to B, and 3 maps to C, and 4 maps to C, well, we do have one input. Every input is used, but not every output is used. And also there are 2 inputs that correspond to 1 output. So it's not an injection because there's 2 inputs that correspond to 1 output. And it's not surjection because there is not a use of D. There's not an output for an input. So this is not a function. Or this is neither a bijection. This is neither a injection nor a surjection, so it is not a bijection. And yeah, that's just kind of how we refer to these functions. And injections and surjections cannot be inverted, but bijections can. If every input has an output and every output has an input, then we can use a bijection, where if we say that f is a function that maps elements in set x to set y, then we can come up with some type of function that maps y to x. So we can have a g that maps y to x. If x to y is a bijection, then there is an inverse that is also a bijection. And the function x that maps to y is considered a bijection Well, in formal terms, it's considered a bijection if and only if. This is if with two f's. For every y in the set of outputs, there is a unique x, which is what we said. There has to be one input for one output, so unique x in the set of inputs, x, with y being a function of x. And already you can probably see some applications of this elementary set theory in algebra, and we are going to extend our understanding of set theory within algebra by talking specifically about the natural numbers. So we're going to go a little bit out of our original description of set theory. I would be willing to talk about some like infinite ordinals and like cardinals, but I don't, I have to admit, I do not know as much as I would like to know, so I'd have to do some more research and see if I can truly understand it, because if I don't understand something, I wouldn't be like comfortable talking about it. So let's talk more about, number theory and like how set theory can be seen as the foundation of like our mathematics. So I'm going to actually look at the axioms of the natural numbers. I have them pulled up right here. So the axioms of natural numbers, they have quite a bit of different axiom like ways that they're written. I don't know how to say that. So there are the original axioms, the piano? I don't know. Peano axioms. It's developed by some type of an Italian mathematician in like the 1600s or something. But there are lots of non-standard ways to like write them and to actually like see them. And the way that I was taught, we use like the actual like math shorthand. So I'm going to show it. We're going to do, these are like things that you've almost definitely seen before. So if you haven't seen them before, they might just seem intuitive. We have for every x, y, and z in the set of natural numbers, when I say membership n, that n is natural numbers, and we're going to show a proof of why this is countably infinite and this is countably infinite, and that is not countably infinite. So yeah, we're going to have some fun with infinite sets in just a little bit, but we need to first start talking about, natural numbers. I think, well, the way that I learned it was the first one is the associative property, that is for every x, y, and z that is a natural number, x plus y plus z is equal to, not parentheses there, is equal to x plus y plus z. So these are some of the ways that we define addition, and we have x. I'm not going to erase this because this is going to be like our introduction to the idea that we want to communicate, and then we can also say that for every x and y, there is no z in this one. X plus y is equal to y plus x. So we have both the commutative and associative properties down. And then we have the idea of distribution. So x times y plus z is going to equal x times y plus xz. That's another important one. And, there is an element 0 where x plus 0 is equal to x. And x times 0. This isn't considered an axiom, but there are, like, I think there's something that does say this: x times 0 is equal to 0. And then there exists an element, 1, in natural numbers where x times 1 is equal to x. So, well, the definition of multiplication is considered just repeated multiplication, repeated addition. So some of these axioms also work with multiplication. And I think, yeah, this isn't considered an axiom, but there is also the idea of less than. So x is less than y if and only if x plus some z is still less than y plus some z. And that also works for greater than. This isn't considered an axiom, but it is just an idea that we have about mathematics. And as you can see, these are some relatively obvious things that we can do with math. We can, repeat addition, we can use addition, and addition is associative and commutative. These are just ideas that you have definitely seen before and used before, but having them formalized and standardized is obviously very important for when you try to prove stuff. So let's talk about infinity. And I won't be using formal proofs. In fact, I encourage you to find some formal proofs on your own, or even try to make your own formal proof. In fact, I'll actually ask you to look at some more accurate axioms. Like, if you see the actual axioms that you can cite, then that would definitely help you in writing your own proofs. But for now, I just want to introduce you to the idea of set theory because, again, set theory is an incredibly broad field of mathematics, so I can't, as I'm still technically basically a child, I can't really standardize all of set theory for you, but I would like to. But I can't. So I'm just gonna introduce these ideas. And another idea that I want to introduce is the idea of infinity. Infinity is weird because this is the set of natural numbers. It goes 1, 2, 3, and this is another thing. You might see that 0 is considered a natural number, and other set theory, 0 might not be considered a natural number. For this, I'm going to kind of flip-flop because I've learned both in the classes that I've taken and, outside study, how, 0 could be considered a natural number, how it could not be considered a natural number, and, what are the different schools of thought behind them. But the way that I learned, 0 was not considered a natural number, even though I don't think that's accurate at this point, but we're going to simply show it. So we have the natural numbers that go from 1, 2, 3, 4, 5, 6, and on and on. We have z, or the set of integers. So that's going to be, dot, 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 a bunch of negative numbers, and then you get to negative 5, negative 4, negative 3, negative 2, negative 1, 0, 1, 2, 3, 4, 5, dot, dot, dot. And then we have the rational numbers. And that goes, 1, 1/2, 1/3, 1/4, and on and on and on. And then eventually, you'll get to 2, 2/3, 2/4, even though 2/4 will cancel out, 2/5, 2/6, and on and on. And it might shock you, but all of these technically have the same cardinality, and that is Aleph null. So Aleph null is, I'm going to erase all this. So Aleph null is considered the first infinite cardinality. There's a bunch of infinite cardinalities, and we'll talk about that. But remember, cardinality is the number of elements in a set, and this is the first of these infinite cardinalities, which means that we are able to count how many numbers are in there. there is countable versus uncountable infinity. And uncountable is what it sounds like. There's no start, there's no end. There's just numbers, an infinite stream of numbers, all of which have no ending, no beginning. It's just a stream of digits that no human will ever even be able to start counting. But countable is what it sounds like. You have a start even though you don't have a set ending, and this is called Aleph null or Aleph naught. It looks like a weird N. That's honestly a pretty that's a pretty good Aleph null. I was about to say. Um, but yes, this is Aleph null, or the first countable infinity. You know, there are higher degrees of infinity with like numbers other than 0, and those will be uncountable. But let's talk about countable infinity while we can. It might interest you, but the number of elements, or the cardinality, of the set of natural numbers is equal to the cardinality of the set of integers, which is also equal to the cardinality of rational numbers. All of these have the same cardinality because each and every one of them is countable. Now, you might be thinking, that doesn't make any sense. Z is the set of integers, and since you start at negative numbers, I mean, you should just not be able to go and do that, right? But mathematicians are tricky. They essentially say that you're not allowed to use common sense when you're thinking in terms of infinity. Common sense doesn't have any place here, it's strictly math. And if it takes you an infinite amount of time to count every natural number, since you are able to start it, that is considered the lowest infinity, but you can also start counting z. You can also start at 0, and I'll actually show you why the set of integers is considered countably infinite. And you can also count every fraction. So that's what a rational number is. It's just a ratio from a to b. So, you know, a over b, for every a and for every b that is a natural, not a natural, for every a or b that is an integer, we can even write that for all a b in z, a over b is in q. Now that I'm thinking about it, I didn't actually define subtraction. That's because subtraction isn't a nice function. Even negative numbers are a little bit tricky, but I think we'll get to that when we talk about why z is considered the same cardinality as n. So let's talk about the cardinality of n. What do we define as countably infinite? Well, let's start with one of our axioms. There exists for all x, y, and z, or for all x, let's say at this point, for every x in the set of natural numbers, or for every natural number, there exists an element 1 where, or such that 1 times x is equal to x. And 1 is also in the set of natural numbers. And I almost forgot one of the most important axioms in the set of natural numbers. Any addition or any sum, so for every x and y in n, x plus y is also in n. So the sum of any two natural numbers is a natural number. It seems obvious, but that's a very important axiom in the axioms of natural numbers. So if x plus y, if we know that there has to be an element 1 in n, or there is a natural number n, that is 1. And we also know that the sum of any two natural numbers is a natural number. Then we can start with the idea that 1 is a natural number, and then 1 plus 1, or the sum of two elements, also has to be a natural number. This we can write as 2, and then 2 plus 1 is also going to be considered a natural number. And you can just keep on doing this. And you will never stop, obviously, but every subsequent, every subsequent number, or every subsequent element in the set of natural numbers, will have another natural number that comes after it, which is that natural number plus 1. So that's why the set of natural numbers is considered countably infinite. It does have a start, it does not have an end, but each subsequent element, we can say, is a natural number. So, yeah, I mean, like, that's not a formal proof, and I actually kind of want you guys to go and look for some formal proofs. If you don't want to do that research, I think I might put some sources down below, but it is very important to take a more, like, active role in learning set theory, because it's so broad that you can kind of do what you want. As long as you're accurate, it's definitely possible for you to discover things that haven't been, like, thought of before. If set theory is the mathematical study of math, there is lots of opportunities to try and come up with something completely new. But you do have to start at the basics, and this isn't, like, the best video for that kind of thing, but it does, I hope it does give some type of, like, introduction to the ideas that are fundamental to set theory and to math in general. So, yes, the set n is the set of natural numbers, and it is considered countably infinite because it does have a beginning, and you can individually count every single element of n, because we know that there is one element 1, and we know that the sum of any two elements in n is a natural number. So you can just continually fill out every element in n with another natural number, which is the previous natural number plus our first element 1. And on that note, we can talk about z. This, I'm actually going to use even less of a formal proof and just say the cardinality of z is equal to the cardinality of n, because of the same reason why n is countably infinite. You can start at 0, that'll be our first element, then you say 1, 2, 3, 4, and for the same reason that we had in n, each subsequent element will be the inverse of, or not the inverse, each subsequent element will be part of this set, but this isn't the correct way to write this axiom. In fact, this will be your homework to find out why this isn't perfect, because subtraction is very difficult to define. It's so we will define subtraction as for every x in n, there exists a negative x, where x minus x equals 0, and minus x will be that value. There's definitely a way to write that better. It's just x plus 0 is equal to x, and then maybe you can subtract x from both sides, or something like that. There is definitely a way to write that in a more suitable way, because you want to write it in terms of addition. That's our fundamental, like, start to all mathematics, and if we can write subtraction in a more sound approach to addition, something that we already know exists, then we have a much better start in understanding what subtraction is. But you guys know what subtraction is, so I don't think I need to explain why subtraction works, but I do want you to see why subtraction works. I might actually, I'm not sure if I should find a good proof for subtraction. I mean, like, I imagine there's definitely a way to even explain it in terms of sets. Like, subtraction in terms of sets is B, let's say you have A minus B. If every element in set A is subtracted by every element in set B, what's left is the elements that are not common to A or B. So it's like the elements in A that aren't common into B. That's the better way of saying it. But there's definitely a way that we can use actual set theory to define number set theory and say why subtraction works. But I mean, if I do think that there is a need for that, I'll make a different video. But yeah, we can define x plus, let's even say y. So for every x, y, and z, there exists a y such that x plus y equals 0, and y has to equal negative x or something. That might be a slightly more appropriate way to define subtraction, but we know that for every positive number, there is going to be a negative number. -2, -3, -4. In fact, this is a bijection. If you can connect those, you know that for every set, or for every input in x that we can map to y, every input in x is just going to be every input in n. We can map that to y, which is also going to be just another like set of numbers that are in z, but it'll have the same elements as the n, or it'll have the same cardinality. Oof, this is gonna get weird. It's gonna be a subset of z that has the same cardinality as z, because z has the same cardinality as n. Now it's getting a little bit crazy, but there is a subset of z that is less, or not objectively less elements, because we can't actually count and see if there's less elements, but we know that there is a subset of z with only the negative numbers. I'm gonna write that as negative n, even though that's not correct. And this is a bijection because every element in n has a number where f of x is going to equal negative x, and y is equal to f of x if y is every element in big Y and x is every input element in x. So yes, this is a bijection. And yeah, we can just say that if we have a function such that every natural number has a negative natural number where x plus y equals 0, then y would equal negative x, then you can count every natural number by the same reason that we could in, not really our proof, but in our discussion a little while ago. And we can also count every negative natural number based on that same discussion. And if you just start at 0, then we have a beginning, but we do not have an ending. So this is considered a countable infinity. So now we know why the set of integers is countably infinite, because you can start at 0, then use every single natural number, positive natural number, and then you can also have the negative version of that natural number over and over again. So now we can talk about the rational numbers. Let me see. Okay, so we also have, I can't write this cube properly. It's like, it's a circle, and then it's a circle in between, and it's like that. That's the symbol for the set of rational numbers. I'm actually going to go back and talk about Cartesian products for a little bit. So we said that a Cartesian product is simply a product, or a set of ordered pairs. Let's write that down. A Cartesian product is set of ordered pairs. We call them CDs, where C is in A and D is in B. And that would be the Cartesian product of A times B. So we can write our set of rational numbers. I'm actually going to include the negative rational numbers as well, but we can say that there is a function phi, or that's not phi, that's a, that looks like the null symbol. Let's say f, actually. Yeah, let's say f. There is a function that maps q as the Cartesian product of every element in Z times every element in N, which means that for every P over Q in the set of rational numbers, because we're defining a rational number as a ratio between two numbers, then the function of P of Q is going to be an ordered pair in this Cartesian product. So P will be a integer and N will be a natural number. So you will have a negative or positive number up here, and you will have a positive natural number in there. So yes, this will be an ordered pair, and this is going to be the Cartesian product between these two. And this will be every negative, positive fraction that is possible. And oops, this is clearly injective, as every single element in PQ does create a rational number. It does have an output, and there's a proof that I find kind of interesting. I'll actually talk about it a little bit. That is, the Cartesian product of any countable set is going to be countable. That might seem obvious, but we will have to, well, we're not going to use a formal proof or anything, but we will have to understand why it is. Alright, so in order to prove that the Cartesian product of countable sets is countable, we need to first start with a corollary, or something that is kind of like an axiom in that we assume it to be true, but we don't have to prove it, and it only applies to our specific proof. So our corollary for this proof as to why Cartesian products of countable sets are countable is quite simply k is an integer such that k is greater than 1. That's just something that we have to assume. And then let's say that S1, S2, and then dot dot dot, all the way up to SK, these are all countably infinite. So S1 is equal to that aleph null, and all of these sets are countable. Alright, and then let's say that we can say, so let's say so that we can say, we know that since S1 is countable and N is countable, there is one element for every element in N, which means that you can write an a function, fi, that maps every element in Si to the set of natural numbers N. So for f of 1, you can map every element in S1 to N. For f2, you can map every function in S2 to N, and on until you get to, Sk. And then you can also describe the mapping of g, some other function, as the mapping of S1 times S2 times Sk, well, not times Sk, but times a bunch of other sets until we get to Sk, and this will be the mapping of n to the power of k, and I guess that makes sense. If we think about it, if we map every element as the Cartesian product of every set that is in between 1 and k, then there will be n to the power of k elements or ordered pairs that we are going to have to create n to the power of k outputs for our inputs. So yes, this will be a mapping of every Cartesian product possible, and this is defined for every xi in Si. So every element in Si fits that bill, and then we can say that g, like using that same function, we can say that g x1, x2, and on up to xk, or the ordered pair of every x element in every set is equal to f1 of x1, f2 of x2, and on and on until we get to fk of xk. So it will be the ordered pair of every output of an x that follows in our g function. So that's going to be injective, right? Using what we know about countable sets, we know that a bijection from a countable set to a countable set is, by definition of a bijection, it's going to be injective. And then we can also say that, let's say that P1, P2, and then on up to Pk are the first k prime numbers. Alright, and so if these are the first k prime numbers from the fundamental theorem of mathematics, we can define, or not mathematics, arithmetic, sorry. Well, let's actually talk about that for a little bit. This isn't going to be too long, it's pretty self-evident. For every, I'll even say for all, n such that n is greater than 1, n can be expressed as the product of one or more primes. So this is up to the order in which they appear. You can't have like 3 be before 2, So I think it's pretty obvious. Prime numbers are obviously the product of themselves, so whoops, they are obviously the product of themselves, so that's why prime numbers fit in with the fundamental theorem of mathematics. I don't know why I keep saying mathematics. It's the fundamental theorem of arithmetic. So yeah, that's relatively obvious, but by the fundamental theorem of arithmetic, we can map every function in n to the power of k to n. Since n is going to be countably infinite, we can say that for every element in a countably infinite set, we can also map that to another countably infinite set. This is getting a little bit weird, but this is a bijection. As we said with z and n, even though n to the power of k might seem like it has more elements than n does, since it'll take an infinite amount of time to actually count n to the k elements, and since we know that there is a starting point, but we don't know where the ending point is, theoretically, there is the same number of elements in n to the power of k as there is n, so we can create a function, and we can say that this function f of n1, n2, all the way to nk, or, every n value in big N, or every natural number, there will be a prime number, p1 to the power of n1, p2 to the power of n2, and then, well, not powers, but you know what I'm saying. Like, there will be a prime number that corresponds to every natural number. So this will be pk n k. All right. And this is going to be an injection. Every n has a p that corresponds to it. And since the composite of injections is an injection, well, I mean, that I think is relatively, normal. It's just like, uh, I mean, the composite of injections is an injection because if we consider every like possible ordered pair of an input and an output as an injection, then there has to be an input for every output. And if we compose two injections, which we know has an input for every output, then all of our combined inputs will still have an output. So I think it's relatively, you know, self-explanatory, but we define G as a countable set of, the Cartesian product of every single set in S1, S2, on and on until we get to Sk. And then we also defined G as the function that maps certain elements in n to the k. So let's actually write down everything that we've done. So we define G as S1 times S2, on and on, till we get to Sk, and this maps to Nk. And then we are able to also map f of Nk to n by saying that this function just maps every element in n to the power of k to a prime number in n. And since this function f and this function g both are injections, because I mean every input does have an output, we can say that since if you compose, I don't know what's happening. Okay, so since you can compose these two functions as f and g, not fog, but f times g, that might be, a more pleasing way to look at it. We can say that f times g, or the composite of those two functions, is going to be the mapping of s1 times s2 times on and on, all the way to sk. That will map to n. So as you can see, g maps to n to the power of k, and f maps n to the power of k to n. So by that logic, if you compose f and g together, you will get a injection that maps all the way to n, which means that f times g, or the Cartesian product of f and g, which are two well-defined sets, the Cartesian product of f and g, which are countable sets, or countably infinite sets, since it is, every set that's possible within k and, n to the power of k. So these, they don't have to be countably infinite, but they are countable sets, and we know that we can map every element in these countable sets, or the Cartesian product of these countable sets, to a countable set n, which we know is countable from that like pseudo proof that we did a little while ago. So yeah, I mean, that might have been a little bit confusing, but I hope it made a little bit of sense. Like, it's just essentially we defined two sets, and then we said that since both of those sets are injective, and since the composition of two injective sets is injective, we can say that by that logic, any Cartesian product of any two sets that are countable will have a countable Cartesian product. So let's go back to our original proof, where we define a function that maps every element in Q to the Cartesian product of z times n, where for every p and q, the function of p and q is going to be the ordered pair of p and q. So that's just saying if we have a function that essentially defines the rational numbers, which again, if a and b are natural or not natural, if a and b are integers, then Um, uh, you know, if a and b are integers, then a over b should be a rational number, and this is going to be injective. You know, every element of p and q, because we define for all p and q, every element in our function is going to have an output. There is no way to organize p and q in such a way that you don't get an output. So yeah, I mean, this function is going to be clearly injective, and we have to assume that by our idea that the Cartesian product of two countable sets is countable. By this idea that we sort of kind of proved. I don't think I gave that proof enough justice, but we kind of understand why the Cartesian product of two countable sets is countable. We can say that z times n, or the Cartesian product of these two countably infinite sets, is going to be countably infinite, and this says that um, the function that defines rational numbers is going to have a countably infinite number of uh, of outputs. So by that logic, Q has to be countably infinite. We can count the outputs for every input because we can count every input. So yeah, I mean, that's relatively, normal. Um, we can actually even, formalize that idea a little bit. This is one of the first proofs you are going to see, and that is the domain of injection from a countable set is countable. So if X is a set and Y is a countable set, if F maps to X from, I mean, if F maps from X to Y, and this is an injection, then X needs to be countable. This is a relatively normal proof. We are going to say that since Y is countable, since Y is countable, it's not small y, I don't know why I wrote it like that, but since Y is countable, you can write a function g that maps every element in Y to some element in the set of natural numbers by the idea that the composite of injections is an injection, which we talked about a little bit earlier. G times f, or G composed with f, maps from x to n as well, since f maps x to y. So yeah, if f maps x to y and y maps to n, then x can also map to n in this composite of f and g, which means that since this is an injection, f composed with g is an injection, every element in x is corresponding with some element in n, and this is, well, I mean, not every element in n has to correspond with every element in f, but every element in x corresponds to something in n, which means that x is also going to be countable, which is why we are able to have that final idea in why q is countable, in that the domain of an injection from a to a countable set is countable. So that's why with that function, for every p of q in q, the function that we defined of p and q maps to some ordered pair of p and q. Since this is going to be countable, this function needs to be countable, which means that this function, which we define as the function that we define as the function that defines the set Q, we can say that since PQ, the ordered pair PQ, has a countable number of possible variants, then this function is going to have a countable set that corresponds with it. So yeah, that was a little bit uh, weird, I know, and I don't think I gave any of those ideas the justice that they deserve. Set theory is simultaneously very crazy and also very interesting. And yeah, I encourage you to go out and find some more set theory. But, oh, I forgot one proof that I actually really wanted to show you, and that is even though we say that n is countably infinite, it has a cardinality of Aleph null, and z is also countably infinite, which means that it also has a cardinality of Aleph null, and q is countably infinite, so it also has a cardinality of Aleph null. The set of real numbers is not countably infinite. This is Aleph, I think it's Aleph 1. I think that's how you're supposed to refer to it. Um, yeah, it's just Aleph 1 is going to be how I refer to it. And this proof is going to be not as crazy as Q, but it's going to be a little bit weird. So yeah, let's get into it. So for this one, we are going to actually have to do a proof by contradiction. A proof by contradiction is exactly what it sounds like. We have to assume something that we want to be false, and then we prove why this assumption could not work, and then by contradiction, the original assumption doesn't work, so the original theorem is proven true. And we are going to prove that the set of real numbers, we'll even constrict it to just the real numbers between 0 and 1 on an xy plane. If you have 0, 0 as the origin, and then x equals 1 as the end value of our interval, this open interval from 0 to 1 has an uncountable. Oh, I wanted to write uncountable in between 0 and 1, but like that's not enough space. Let me actually do this one more time. On an xy plane where we have 0 as the origin and 1 as that point right there, and our interval is 0 to 1, then every x in between, this interval has an uncountably infinite number of possible x values, of possible real x values, I should say. Not writing this correctly. Uncountably infinite real x values. So let's assume that this is untrue. Let's assume that we can count every real number between 0 and 1, and if that's true, we are able to come up with a function that maps every element in n, because n is countably infinite, so if the number of real numbers between 0 and 1 is countably infinite, we can create some kind of a bijection where every element in n corresponds to every real element between 0 and 1, and every real element in 0 and 1 corresponds to an element in n. This is going to be a bijection for the sake of contradiction. And we can say that every n in n, so we're going to start at 0 for this one. We're going to have n equals 0. This will map to 0 point a 0, 0, maybe. And then a 0, 1, Actually, let me, uh, hmm, I don't know what way I want to write this. You know, it doesn't matter. Um, sorry. A 0 0, and then A 0 1, and then B, I keep writing B, A 0 2, and then on and on and on, and then 0, the natural number that comes after 0, 1, maps to 0 point A 1 0, A 1 1, A 1 2, and 2 maps to 0 point A 2 1, A 2, not A 2 1, sorry. It's going to map to A 2 0, A 2 1, and A 2 2. You might be wondering what A in this case is. This is going to be our digits. So what I'm essentially saying here is that if this mapping of every element in n to every element in between 0 and 1 is possible, then you can map every element, 0, 1, 2, 3, on and on, to 0 point some a, or some digit, and then on to A01, A02, A03, A04, and that would be a countably infinite number of possible values, theoretically. And then you can also do that for every single natural number 1, natural number 1, 2, 3, 4. You can just keep on going further and further. And we have to prove now that if this idea that we can map every element in n to 0 point some assembly of digits, we have to say that if this is not a bijection, then this is not a surjection. That means that every output is not corresponding to every input. So the cardinality of n cannot equal the cardinality of the number of real numbers in between 0 and 1. So this cardinality of the number of real numbers between 0 and 1, this has to be quote-unquote larger than 0 and 1, because n is considered the smallest infinity, right? It's Aleph null. So let's try to argue that this is not a surjection. So we need to find something that the number that we create in our function f doesn't actually fit in with how we defined f. So in order to come up with some assembly of digits after that 0 point that does not fit in our function f, we're actually going to have a bit of an issue, because real numbers can be written in different ways but still have these same values. For example, the infinitely repeating 4.9999999 is the same as 5.000 with these zeros repeating. So we're going to have to ignore our 9s, and we're just going to focus on an infinitely repeating number of zeros. So let's define our sequence, and we'll say that our first instance of our sequence is going to be I. That'll be our first instance, and that starts at 0. And we can say that B of I is some kind of a, well, I don't know how to explain this without getting too confusing. This is a relatively confusing proof. So let's start with A00. A00 is obviously going to be, our first element in AII, which is supposed to be some type of, potentially infinite number of AIIs can exist. A00 is going to be our first number, and we want to make a decimal that does not fit in with A00 or AII, right? So if we want to make something that does not have AII, we're going to have B0, and we don't want A00 to equal B0. Again, remember our decimals are defined as, 0 maps to O point, A00, A01, on and on and on, and then 1 maps to 0.A10, A11, and on and on and on. And we want to have AII and AII, and we want values that are completely different from A00 and A11 for B0 and B1, where if we assemble, a number B that maps to B0, B1, B2, and A00 does not fit with B0, and A11 does not fit with B1, and A22 does not fit with B2, then we will have created a completely new decimal that is not defined by F, right? So let's do that. We will define this idea where AII cannot equal BI. And let's say that if this, I don't know how to formally put this into math terms, but essentially let's just say that if AII, or let's say that our first element A00 cannot equal B0, that means that if A00 is like 1, then, if A00 corresponds to 0, then B0 will correspond to 1. And if A00 corresponds to 1, B0 correspond to 2. And then, on and on, we will eventually cycle through every single digit number because, again, since this is a supposedly countably infinite repeating decimal, there is only 10 possible digits that it can go through, and after 9 it'll cycle back. So by that logic, we can define B0 as some number that is not A00, and we can define every AII as something that does not fit with BI. And now we have defined a sequence B0, B1, not B, BI, B1, B2, B3, and we can say that since B is still a number, we can actually map it. We can do an F of B, where B is going to be in natural number n, and we will have 0 point B0, B1, B2, B3. And remember, AI, or A00 in this case, A11, A22, A33, these do not equal one another. Since they do not equal one another, this sequence, 0 point B0, B1, B2, B3, B4, and on and on and on, is a completely unique idea, It's a completely unique number that still does fit with n, which means that there is an output that does not correspond to an input, which means that while f may be injective, it is not surjective, and since a bijection is both a surjection and an injection, the set of r, or the number of real numbers in between 0 and 1, is uncountably infinite. And yeah, that's pretty much it. More informally, you might have seen this proof as, say, if you have 1.010 and on with like some random assembly of zeros and ones, you can always create, or let me erase that 0. If this never ends, if there is no terminating point where this 0 becomes, has a endlessly repeating 0, then you can actually, flip every 0 for another 1, and you will have created a completely new decimal. So, yeah, that might be the start to a proof. You might want to even look up that kind of a proof, see why why R might be uncountably infinite using decimals. Okay, I swear. I literally just erased it, 0.010. And if there, is an infinitely extending number of zeros and ones that are, randomly repeating or not repeating, and there's no infinitely repeating 0, there's no termination, because that's what a real number is. It's just a decimal without a terminating final value. That means that you can have another decimal that is also another real number, where every other value is going to be a 1 for every 0, and every 0 is going to be a 1. And by that logic, you will be able to create a real number forever in between 0 and 1. So that would make the number of real numbers in that interval of 0 to 1 uncountably infinite. So yeah, that's not a proof. That's just an idea that you might want to think about. And I understand that this video wasn't the greatest video in introducing you to set theory, but I hope it made you curious, because that's all you really need to know. Curiosity is what's going to take you where you need to go, and set theory is very interesting to me. And obviously, I'm not an expert in set theory, but I'd like to be. So I'm going to link some of my sources down below. I want you to do some research on set theory and to learn more, and maybe even comment down below, where was I inaccurate, where I could have done better. This is as much of me learning this as you are learning this, because I had to actually, do research for my recording, which is something that I don't tend to have to do. So, that was today's episode of How to Understand X. We're going to end with an album recommendation, and that is Kamasi Washington's The Epic. Now, this is his 3-hour magnum opus, and it's a lot. I won't lie to you, it is a lot. 3 hours is a long, long time, but it is an essentially perfect 3 hours. It's just beautiful. It's just beautiful. I can't really, describe it any further than that. I won't lie and say that it's for everyone. I don't want to sound pretentious. It's not like super niche, but it's definitely not for everyone. And if you listen to maybe the first 10 minutes and you don't like it, then you are not going to like the next 2 hours and 50 minutes, I mean, just try it out. If you do like it, that's fantastic. Comment down below what you think. If you do not like it, you can also comment down below what you think. And, yeah, that's pretty much it. Let's say your exercise for now is going to be do some let's say do some jump squats. There we go. And if you like this video, please comment down below. If you did not like this video, constructive criticism is always encouraged. And if you're not in the mood for, oh man, I forgot my outro. It's, if you're not in the mood for constructive criticism or a comment, then you can you can do a jump squat. All right, bye.